I suppose we can get this show on the road. We still have a few people trickling in. I think there are about 3-ish people missing so right now. But yeah, as most of you know, I can't actually stay for class today, and I actually have someone here to fill in for me. This is John Adamski. You should be able to see him on your screen already. John and I go way back. We're good friends. He's a good instructor. I feel very safe leaving him in your hands. So the plan for today, he's going to go over the quiz with you, the quiz you just took, and then he'll let you go. I suppose, of course, if you have any general questions, you can ask him as well. If you have any questions about this class specifically, I do know some people joined the class very recently. I was actually trying to force new kids into the quiz just now. But any class specific, any questions specifically about this class, I'll answer those. Just shoot me an email. Some of you I know I need to get up to speed. But any general math questions, I suppose you can ask John. He'll go over the quiz. And just remember that today, you guys should be watching up to lecture 5 by the end of the day. That being said, without further ado, John Adamski, take it away.
All right, thank you very much.
Okay,
thank you.
So I'll get out of your here. Good luck, everyone. Have a good day. I will actually see you guys next week.
All right, have a good one.
Take care.
All right, so guys, my name is John. You can call me John. I'm just going to go over this quiz that you just took with you. If you have any questions, just ask. I'm going to warn you that I'm not the best at looking at the chat. I will try to keep an eye on the chat if you ask there, but I encourage you to turn on your videos and turn on your microphones and ask me verbally what your questions are. So I'm going to start sharing my screen here. What is that noise? Okay. All right, so this is the test you took. Oh, we keep having to admit people. Okay. And I'm just going to go through this one at a time. And like I said, if you have questions, just ask, okay? All right, so let's see. I guess you're being asked about some exponential rules here. But they're usually presented in a different format. Like if I look down here, I usually see a rule that says that this would be, oh, no, that's not what I'm trying to say. I would usually see a rule that says that this is equal to a to the x minus y. This is when I subtract my exponents, okay? And there's another rule that would say that a to the x times a to the y. This is when I add the exponents. And there are other rules too. For example, there's a case when I multiply exponents. That's a to the x inside parentheses to the y equals a to the x times y, okay? And that's the rule that I'm going to be using here. So the way I'm going to think about this is I'm going to think of this as a to the x being multiplied. Maybe I'll begin by saying this. I know you all know, but x over y is actually equal to x times 1 over y. So that's simple, but very helpful in this scenario because now I can write this as a to the x times 1 over y. And I can utilize this rule here that tells me, reading from right to left, okay, when I have a base raised to the product of exponents, like I do in this rule, I can split it up and call it and treat it as nested exponents. So I'll do that. I'll treat it as a to the x raised to the x power first, and then take that answer and raise it to the 1 over y, okay? And then I understand that there is a rule that when you raise anything to the 1 over n, that is by definition the nth root of a, okay? It's the thing that when you raise it to the nth power, you get a, right? So anyway, this is the yth root of a to the x. That's your answer. So that would be that choice right there. Okay. All right, moving on. It's another rule, and actually I've already gone over this rule when I showed you this exponential rule. We usually read this from left to right, but of course you can read it from right to left. And what that would say is that this is equal to m to the x times m to the y. Okay, that's just a basic exponential rule. So is that a choice here? Yes. Okay, cool. And a to the negative n. All right, so by definition, when I raise something to a negative power, that is equal to the reciprocal of a to the n. Okay, it really does make good sense. If I have a, and I have a squared, and I have a cubed, okay, etc. How do you get from one term to the next? Well, I'm multiplying by a, correct? Multiply by a, multiply by a, right? That's the pattern. And you can extend this pattern to the left, right? So if I want to go from right to left, what I'm doing is dividing by a, right? And so you've got a to the first here, if you like. And by just extending this pattern of division, okay, I can make sense out of not only negative exponents, but an exponent of 0 and stuff, and all of that good stuff. So I'm just dividing by n. Okay, now we know that a divided by a is 1, so I've got 1 here. And that means that a to the negative 1 is 1 over a, 1 divided by a. And this is that divided by a. So we've got the definition of negative exponents just follows from this pattern of dividing by a as my exponents decrease by 1. Okay, so this answer, I'm looking for 1 over a to the n, and I see it right here. Okay, m squared minus n squared. This is called a difference of squares. So you could factor this and call it m plus n times m minus n, okay? To go from the right side of this equation to the left, you're just distributing, okay? Or you could say you're foiling, right? You have m times m, there's your m squared. N times negative n, there's your negative n squared. And then your other products here, let's see, what do you have? You have a negative mn and a positive mn, those cancel, leaving you with just m squared minus n squared. Okay, so I'm looking in the list for this expression. I don't see it. This expression in the fourth choice is a little interesting. It's a radical expression. I could rationalize the denominator, okay? I could multiply the top and the bottom by the square root of m minus the square root of n. Okay, and what would that do? Well, the top would become m minus n times the square root of m minus the square root of n. I'm not going to multiply that out. It's going to become a mess. The bottom actually is nice, okay? If you follow what I wrote up top right here, this formula that shows you what happens when you multiply, the sum of two terms times the difference of the same terms, you get actually a very nice answer. So on the right-hand side here, that's, by the way, that's what's going on. I've got the sum of two terms multiplied by the difference of the same two terms, okay? That's actually going to turn into the first term squared minus the second term squared, okay? Which is actually m minus n. So I think I'll just cross this out and write that that's m minus n. And so there actually is some cancellation here. Okay, I can cancel the common factor of m minus n. And I'm left with a simple expression, but it's not the one that I started with. Okay, so that one is not the correct answer. The correct answer is none of these. Okay. No questions so far? Okay. So now you've got this expression that has a negative exponent, and you also have a coefficient out front. Okay. Now, when I teach exponents, I usually tell students that exponents only act on what they touch. Meaning that this exponent of -2 is not touching the 5. It is touching the x, but it is not touching the 5. And so what you have here is 5 times whatever x to the -2 is. Okay? And so another way to write this, there's nothing you can do with that 5. Okay, it's just a 5. But the x to the -2, we could write it as 1 over x squared. Okay? And then you could write it as 5 over x squared if you like. Okay? And I'm looking for that as a choice. That is a choice. If you wanted, this one, I think this one is a tempting answer. Okay? But this would be 5x to the -2. See, what the parentheses do is they treat, they turn everything inside into one object. Okay? 5x is two things. It's two factors. It's a 5 and an x. And if you want the exponent to act on both of them, then you have to group them together with parentheses. Does that make sense? This would be 5 to the -2 times x to the -2. And that would give you 1 over 5 squared times 1 over x squared. And that would give you 1 over 25x squared. Okay? Okay, and now we have the coefficient of x in parentheses with x, okay, all being raised to some power. So now you do have, this is a -1 and an x, and they're both being raised to the -18th power. Does that make sense? The exponent is basically being distributed to the coefficient and the base, x, okay? Now, -1 raised to any even power is just 1. So this is just x to the -18, which we know is 1 over x to the 18th power. Okay, so I'm looking for that as an answer, and I see it. It's the first one. Okay. Yeah. Any other questions? Simplify the radical expression. Okay, use absolute values where appropriate. Okay. So the rule that we need to use here is that the square root of a product is equal to the product of the square roots. And it's actually not a new rule. This is really just a rule for exponents, because you already know that if I were to have a product raised to an exponent, let's say 1/2, which is the square root, okay, this is a rule for exponents, okay, that the exponent needs to get distributed to everything inside. Okay. But I want to point out that the inside, when I say inside, I mean I'm looking at a product of two things. Okay, it would be incorrect to say that that the square root of a plus b. Okay, that is not the same as the square root of a plus the square root of b. That is false, false, false. Okay. So here I can write the square root of 144, and I can write the square root of y to the 6th. And it might be helpful to remember that that the square root is the 1/2 power, so that you can multiply these exponents together to get y. Well, okay, so let's see. I actually get the absolute value of y cubed. Okay. So the answer here is 12 absolute value of y cubed. Now, why do I have absolute values here? Well, let's just take an example. Let's take an easy example. Let's say I start with, let's just imagine, for example, that y was the -2. Maria, the last two, let's see. I'm not sure which ones you're asking about. I'll just scroll up for a second. Are you seeing what you need to see? Cool. Okay, so if y equals -2, then let's talk about the square root of y to the 6th. Okay, so this would become the square root of -2 to the 6th. Okay, and let's see, 2 to the 6th is 64, I believe. So, so a negative number raised to an even power is, of course, positive. So you're going to have the square root of 64, which I would say is 8. Okay, but that's not -2 cubed. Okay, it's actually, you're getting a positive number. You always get positive numbers from the square root operator. Okay, the square root of anything, is by definition not negative. Okay, it's part of the definition. I know that, you know, when you talk about the square root of 64, some people will say that it's plus or minus 8. That's incorrect. Okay, the square root is by definition the positive number or the non-negative number whose square is equal to that number underneath the radical sign. Okay, so that's a general rule, and this is a little odd because it's y to the 6th, but as a general rule, the square root of x squared, just remember this, is equal to the absolute value of x. You don't get back what you started with if you started with a negative number. You're going to get back the positive version. Okay, so I guess I could just use this rule is all you really need. For this question, I can take this expression that I've written and call it the square root of 144 times the square root of, and I'll just call this y cubed squared, or yeah, that's fine. And then that's 12. And the square root, you want to say that the square root and the squaring cancel each other out, but remember, they don't. You're left with an absolute value sign, because what if y cubed is negative? It could be. So the point is, you have to have an absolute value sign around here to make the answer positive. Okay? Oh, question. So why not, are you asking, oh, okay, I think okay, so I definitely answered why not this one, right? Because it's missing the absolute value signs. Choice number 1, 12y cubed is not acceptable? No, it's not. Again, because if y is negative, that answer is negative. And the square root of something is never negative. Okay? Okay, so now we get on to some exponentials and logarithms. Okay, and let's see, which of the following statements are true? Select all that apply. Okay. All right, well, this is interesting. Now, I don't need, I thought for a second I was going to need to pull out a calculator, but I don't. Because what the statements are, is the statements are, they have these conditional statements that says, if the left is true, then the right is true. Okay? Has Jhevon gone over this symbol? Because that's a very particular mathematical symbol. Okay? So if you write a statement, and then you put this equal sign turned into an arrow to the right next to it, what this means is if P, then Q. Have you guys, I don't know, have you gone over that? I think I've just told you the whole story. But the point is that this has nothing to do with whether or not the left-hand side is true. We're saying if the left-hand side is true, then the right-hand side is true. So in other words, does the left imply the right? Okay, so I can take it for, I can just assume that the left-hand sides are all correct. I don't know, okay? It seems reasonable. But anyway, I think this question is really just getting you to apply this log rule that says that log, let's see, how should I say this? Log of, I need three numbers. I'll say log base A of X equals Y. That's the same as saying A to the Y equals X. Okay, these are equivalent statements. Okay, and the way I usually remember, the way I remember that is I think of just crossing out the logarithm. Oops. I think of crossing out the logarithm and then just switching the positions of X and Y. And then you'd be left with the statement below, A to the Y equals X. Okay, so this is just playing with that. Let's see. So maybe for this top one, and then of course you can work from the bottom one to the top one. They're equivalent. So the equivalent way of saying this is to say that log base E of 10.49 is equal to 2.35, and log base E is ln. That's the definition. Okay, so this first one is definitely true. Moving on, the second one looks very similar. We've got the same, okay, so e to the 1.25. All right, so it's a similar thing. I can change this into log base e of 3.49 equals 1.25. Okay, but that is not what the right-hand side says, so this is not correct. And in the third one, I can do the same sort of thing. In fact, I'll just show you what I really do in my head. I cross out the logarithm and I switch the position of these two numbers. Okay, and I would say that radical 2 raised to the 5.61 is equal to 7. That's not what the right-hand side says. This is incorrect. And in this last choice, same sort of thing. I'm going to cross out the logarithm, switch the position of these numbers. 10 to the 1.23 equals 17. That's true. Okay. So any questions on that? No? Oh, I have a student in the waiting room. Sorry. Okay. Okay, this says which of the following correctly write the given log function in a simpler form? Okay, note it does not have to be the simplest form, just simpler. All right, so we're testing on log rules. We had the log definition, now we've got log rules. This first one is not correct. Okay, it's almost correct, but to make it correct, I would need to have a minus sign here instead of a plus. Okay, the log of the quotient equals the difference of the logarithms. And so we have that log rule, okay, ln of a over b equals ln of a minus ln of b. And in this next rule, I'm going to use another, in this second one, I'm going to use another rule, which is ln of a to the n equals n times ln of a. Okay, so for this first one, the first step would be to use the first log rule I went over and say that the ln of this quotient is equal to ln of the numerator minus ln of the denominator. That would be true. But you can go a little further. Okay, you can write that instead of using the square root sign, you can use an exponent of 1/2. And it's the same thing. So this would also be true, all right? And then I can use this rule that I described over here to just say, to just take this exponent of 1/2 and make it a coefficient. Okay, and now I have this expression. This expression is true. Oops. Okay, is this a which of the following? Yeah, so I do have to keep going. Okay, maybe we can go a little quicker through this one. I see a bunch of stuff. As a first pass, I might say that it's ln of the top. Okay, so the top is x squared times the square root of x plus 1 minus ln of the denominator. Okay, so that would be 3x plus 4 to the 1/3. This is the third root, the cubed root. Okay, that's simpler, but that's not the answer. But these expressions can be simplified on their own, so maybe that's what I need to do. In the first expression, okay, we have ln of a product of two things. Let me get that rule down here. So ln of A times B, this is when you add them together. Ln of A plus ln of B. Okay, so these are your log rules. Whoops. These are your log rules. And I can apply that here to show that these expressions are the same. Okay? On the bottom, you have ln of a product of two expressions. On the top, you have the sum of their individual logarithms. That's cool. And in the second expression, I can see that what's happened is we've applied the rule for exponents, and the exponent was removed from the logarithm and turned into a coefficient out front. All right, so that was an application of this second logarithm rule. This is true. This expression, this equation is true. And what do you guys think about the last one? Is the last one true or false? Let's see, is it false? Let's see. Ooh, okay. I think you're right. I think it is false. Let's see. This one is probably the trickiest of all, I would say. In my first pass, I'd say this is ln of, hopefully, maybe we can see this in one step. So you've got x plus 1 being raised to the 1/2 power. The 1/2 power is turned into a coefficient. You've got 1/2 ln of x plus 1. Cool. Then you have to subtract ln of the denominator. Actually, I guess I'll use exponents. So I've got 3x plus 4 to the 1/3. Okay. Now here's the thing. You're subtracting this entire expression. So if you're going to apply a log rule and turn this into something else, you can't forget that you're supposed to subtract all of it. Okay? So we are going to turn it into something else. We're going to turn this into 1/2 ln of x plus 1, and then we're going to subtract whatever this turns into. Okay? So it's a product of things, so I can turn it into ln of the first factor plus ln of the second factor. And the second factor is being raised to a power, so at the same time, I'll make that exponent into a coefficient. Okay? Now, I probably would have turned this exponent also into a coefficient, but I'm looking at the answers supplied here, and they did not do that. So the point here is that you need to distribute this negative sign to both of these terms. Okay, so this answer that they provided is almost correct, but what makes it incorrect is that this plus sign should really be a negative sign. Is that clear? Oh, it looks like this one generated some discussion in the chat. I thought it would. This is a very common mistake, okay? But one thing to remember, so for every factor in the denominator, you're going to be subtracting a log term. There are 2 factors in the denominator, so you should have 2 subtractions in your answer. Does that make sense? Whoops. Okay. And if you, this has one factor in the numerator, so there's one positive logarithm, and then two factors in the denominator, so two negative logarithms is what you should have. Okay. Perform the following evaluations with exponentials and logs. Okay, this is an expression, this is an important one. In calculus, you get answers that look like this all the time, and you want to be able to simplify them. So basically, the rule we need to understand is that f of x equals e to the x, and g of x equals ln of x. These are inverse functions of one another. Okay, what that means is that e to the ln of x is x. Okay, assuming x is greater than 0, because otherwise ln of x is undefined. Okay, but e raised to the ln of x, you will get back what you started with, assuming you started with something that you were allowed to input into ln. And similarly, ln of e to the x is x, and this is true for all x. Okay, this symbol here just means for all. So anyway, that's what I'm going to be doing here. And the way I apply it to this question is I take this expression of e to the 2 ln of something. It happens to be, what is this? The square root of x cubed, okay? And I'm going to very trivially rearrange this and call it e to the ln of the square root of x cubed. Okay, squared. Now the rules for nested exponents say that you're supposed to multiply these exponents together. And if you know that the order of multiplication doesn't matter. So clearly these two sides are the same thing. But and this is really a cosmetic difference, but what I've done is I've gotten the e and the ln in this position where it's obvious. Oh, e to the ln, those are inverse functions of one another. Okay, if you start with some expression and take its natural log, but then you take its natural exponent, you're going to get back exactly what you started with. Okay, so I'm going to get back the square root of x cubed times 2. Oh, I'm sorry. Squared. Okay, and so let's see. So where am I at right now? Interesting. So I say this is interesting because we've already seen an example today where you took the I see. We're squaring a square root. That's safe. That is x cubed. Okay. Maybe I should be very clear about what I'm hesitant about. So what I said before about where the remember when the absolute value sign appeared in one of the early questions on this quiz? The rule I gave you is that the square root of something squared. Okay, so the squaring function and the square root function are not exactly inverse functions of one another. And the reason is that you have to be careful about the domain, okay? The square root function and the domain and the ranges. The square root function's range does not include negative numbers. So you will never get back a negative number. And so you might not get back what you started with. You're going to get back the positive version of what you started with. But the opposite order, if I were to take the square root of something and then square it, you will get back what you started with. Okay? And really, it's kind of it's not really that big of a deal. If you think about it, of course, what you're going to get back is going to be, I mean, if you were able to take its square root, then you should have started, this should be something positive already, right? Otherwise, it's undefined, and then this is all nonsense. So in writing this down, there are some built-in assumptions. If you have the square root of x, we're going to assume that x is already not negative. So anyway, in this case, you will get back what you started with. You'll get back a positive number for sure, but it's clear that x must have already been positive. Does that make sense? Do you guys need a further explanation as to why there's not absolute values here? And the answer to this question would be x cubed. Okay, so just these are general rules, okay? And these same rules apply to, whoops. These same rules apply to other roots and powers, any even roots and powers, okay? This works for any even power and root. Not just the squaring function and the square root, but if you had the fourth power and the fourth root, the sixth power and the sixth root, this would also apply. All right, let's see, we've got, it says solve. Am I out of time? What time does this class start? End? It's supposed to end at 9:45, is that correct? So how many questions do I have left?
I think you're
I'm
good.
gonna go.
End at like
What's
11.
that? This class goes until 11:15?
Yeah.
Whoa. This is, oh, do you guys only meet once a week or something?
Yeah.
Okay, wild. Well, then I will keep going, but there's no way I'm going to go to 11:15, just to let you know. Unless you guys come up with some good questions, so let me know, okay? All right, so this says solve the equation. Great, okay. To begin with, I guess I can just multiply both sides by 3. I think everyone's clear about that. So I get ln of some expression equals 3 times 2.5. Okay, well that's 7.5. All right, no big deal. Now here's the new tool, I would say. If the left-hand side is equal to the right-hand side, then I can take the base e and raise e to the left-hand side and raise e to the right-hand side. And this is a new equation. Okay, I'm saying e raised to the natural log of 8x cubed is equal to e raised to the 7.5. That makes sense because we're told that the left-hand side is equal to the right-hand side. So of course this is true. The reason I'm doing that is so that I can make a cancellation. Okay, remember we talked about e and ln being inverse functions of one another, right? So on the left-hand side, I'm left with just 8x cubed. And on the right-hand side, well, I don't know what e to the 7.5 is, but it's not that big of a deal. I'll just leave it as e to the 7.5. And the rest is pretty simple. So I divide both sides by 8. I get e to the 7.5 divided by 8. And then I can say that x is equal to, so what I'm doing right now is I'm going to raise both sides to the 1/3 power, which is to say I'm going to take the cubed root of both sides. And that leaves me with, let's see, I can apply a rule so that I take the cubed root of the top and the cubed root of the bottom. So that's going to be e to the 7.5 to the 1/3, take the cubed root of that. And on the bottom, just to show you that there's 2 ways of writing it, I'll take the cubed root of the bottom as well. And what am I left with? Well, that's e to the 2.5. I get back this number 2.5, right? Multiplying these nested exponents, right? 1/3 of 7.5 is 2.5. And downstairs, the cubed root of 8 is 2, because 2 cubed is 8. So that's my answer, and that's what I'm looking for. And that's this first choice. Okay. Any questions on that one? Okay, so this says solve the equation for x. Okay, great. So very similar to the last question. The last question was an equation that had logarithms in it, and I needed to get rid of the logarithm because the thing I'm trying to solve for, you see, is inside of a logarithm. So that logarithm needs to disappear. And the way you get a logarithm to disappear is to perform its inverse function, perform the exponential function that is its inverse. So for ln, that would be e to the x, because the base here is e. In this question, the base is 5. So I'm not going to take e and raise it to both sides, although I could. It's certainly true that e to the left-hand side does equal e to the right-hand side. That's just not helpful because e and log base 5 don't cancel like that. Okay? What I want to do is I want to take 5 and raise it to the left-hand side, and 5 and raise it to the right-hand side, and those are going to be equal quantities. Okay? So when I do that, these functions cancel, okay? And I am left with just x squared minus 10 equals 3x. Does that make sense? Another way to say it is that log base 5, if you are familiar with its graph, if you're familiar with the graphs of any log function, okay, they all look very similar. They all basically look like this. They all have an x-intercept of 1, and then the only thing that distinguishes them is where they reach a height of 1. So they all reach a height of 1 at their base. Okay, so if I want to be really general, this is the graph of y equals log base a of x. Okay? The common bases would be e, being the most common one. The natural base is e. 2 and 10 are also being used. And in this question, we're using 5. It's a little unusual, but it doesn't really matter. Okay, the point is that we get this equation. Okay, and I think you all know how to solve this. So I bring everything to one side. And I write, I factor this as to x minus 5x plus 2, right? And so I get x equals 5 and x equals negative 2, and I'm done, right? So I've got these solutions. Does that mean that the answer is this one? Is this the answer? No. Okay, Daniel, good. Okay, some of you are picking up on what I'm getting at here. Good, I'm going to reject this one. And why? Why is this one not a real solution? It's a false solution. Okay, this one is a false solution. Why? Why is that not a real answer, real solution? This is the answer to the question, and why is that the only one? Because it's negative. Cool, that's correct. You have to, you know, when we went from this initial equation, okay, to this equation, there were some assumptions being made in the first, in this equation, there are some implicit assumptions that are not very clear in this equation, okay? It's true that if you are a solution to this, I'm sorry, if you are a solution to the top one, then you are a solution to this equation. But the bottom equation has solutions that are not solutions to the top, and the reason is that these logarithm functions that we made disappear, they have restricted domains. Okay, this is a polynomial equation. When solving it, there's no restriction on the possible values that x can take. In this one, what we know for certain, we could have said it at the beginning, but there was really no reason to say it initially, is we know that x squared minus 10 has to be bigger than 0, okay? And we also know that that is to say, you can't take the logarithm of negative arguments, right? Whatever this expression is, it has to be at least 0. You can only take log of things that are positive. So let's see, what does that mean? That means that x squared has to be at least 10. And so x has to be at least the square root of 10, okay, which is about 3 point something. I don't know. But it's a little more than the square root of 9. So it's 3 point, I don't know, something. But also, we know that 3x needs to be positive, and that means that x needs to be positive. So actually, negative 2 is a false solution for both reasons. It's both below 0 and below the square root of 10. But luckily, 5 is in the solution region. 5 is a bona fide solution. It's both bigger than 0 and bigger than whatever the square root of 10 is. X equals 5 is correct. Okay. Okay. Next question, solve the following equation for x. Okay, we're still going to require logarithms here. As this first step, I think I'll divide both sides by 3. That seems like the obvious first thing to do. So the left-hand side is e to the 4x minus 5. The right-hand side is 8. Okay, if these are equal quantities, then it should be also true that ln of the left-hand side should equal ln of the right-hand side, right? The reason I'm doing that is so that I can bring this exponent downstairs, okay? Now this becomes 4x minus 5 times ln of e equals ln of 8, okay? I'm doing this in a little bit of a different way. I'm just using a log rule, right? Right? Bringing that exponent out front as a coefficient. Now what I want to point out is that ln of e is actually 1, right? So I kind of said that already when I wrote this. That means what I was saying here when I told you that this point on the graph is a comma 1. Okay, what that tells you is that log base a of a is 1, no matter what a is. Okay, the only restriction is that a needs to be a positive number. Okay, so in this case, what that is this is log base e of e. Okay, it's 1. So this whole equation is very simple. It's just 4x minus 5 times 1 equals ln of 8. And let's see, I can subtract or add 5 to both sides and divide by 4. Okay, so I'm looking for that answer, and I see it. I think it's the first choice, right? Is that clear? Okay, optional bonus problem. Okay, write the symbols and say the limit as x approaches, oh, we write the symbols and say, okay, so this is translation. The limit as x approaches a of f of x is L if, all right, so we're looking for the definition of a limit. This is interesting. So I would guess, I'm not sure how, what he's expecting here. I have 2 possible answers here, okay? Do you guys want to supply your own answer? What would you say? Did anyone answer this? Oh, it's a multiple choice. My bad. Glad I scrolled down. All right, so I guess I'd have to go through these one at a time. When we plug x equals a into f of x, then the output is L. No. The idea of a limit is that x approaches a. So we let x get very, very, very close to a, right? if A, let's just say A was the number 5, then we would plug in numbers like 5.1, 5.01, 5.001, you get the idea. And we'd also be plugging in numbers like 4.9, 4.99, 4.999. And so in other words, letting X get close to A and looking at so as our inputs get close to as inputs get close to A, as input approaches A, the output is getting closer and closer to what number? Well, L, that's what the limit is. I'm not sure if you've seen limits in this class. I think since this is a bonus question, maybe he's just pushing ahead a little bit, okay? But, or seeing who's, taken some high school calculus or something like that, I'm not sure. But the first answer is definitely wrong because we're definitely not going to be plugging in X equals A. Second choice says the output of F is L no matter what X is doing. Nope, that's also wrong, okay? Most functions output depends on the input, okay? This would only be true if the function was constant, okay? Functions that don't depend on their input are constant functions. That's true for some functions, but certainly not in general. The third choice says if X gets close to A from all directions, good, and we had that going on. I was getting close to my example, my value of A was 5, and I was getting close to 5 from above and below, okay? As X gets close to A from all directions, then the outputs get close to a unique value L. That's the answer, okay? We can go through the other ones and say why they're wrong. If X gets close to A from the left side, then F of X will get close to a unique value L. That's almost right, but the symbol for that, if you want X to get close to A from the left, you have to put a minus sign here. Okay, that would be this line here. And clearly none of the above is correct because the third choice is correct. Okay, again, I'm imagining this is a Calculus 1 class, so I imagine you are not expected to have seen limits before, so I'm not going to say any more about them. This was a bonus question, and this is an optional bonus problem. Aren't all bonus problems optional? Oh, yes, the first one was optional. This one is also optional. Okay. Compute the following limits. Oh, okay, gosh. So now we're going above and beyond. And someone's already telling me that does not exist. Cool. Okay, maybe it doesn't. Let's see what's going on here. Well, okay, so this is interesting. So, okay, so you've got this, I've got a function here, okay? I'm thinking of this expression as actually a function. And it depends on X, right? You've got X cubed plus 5 divided by X squared plus 1. And the only reason I'm introducing this letter F is so that I can talk about what the domain of F is. Okay, so that's not calculus. You should know what the domain of F is. I see some good things in the chat. So Daniel, well, let me just get into this a little bit. So let me continue. Let me just continue. What's the domain of F? What's the domain of F? Generally, when you're looking at a function, when you're asked about the domain is you kind of start with all real numbers and then eliminate them as when you find problems. So are there any problems here? Well, the numerator itself is a polynomial. So you can plug any number you want into the numerator. And you can also plug any number you want into the denominator. The thing to watch out for is that if the denominator equals 0, you have a problem. Okay? So in our first step, what I can say is the domain of f is equal to the set of all numbers x such that x squared plus 1 is not 0. Okay? But actually, x squared plus 1 is never 0. Okay? That's all real numbers. Okay? Which has the symbol r. Okay? There's lots of ways you can see that. X squared plus 1 is just like the regular parabola x squared, but it's actually been bumped up by 1 unit. So it doesn't have an x-intercept. It never equals 0. Okay? You can plug in any number you like. And again, I'm not quite sure if this explanation is going to suffice for you, but this function f is continuous. It's continuous everywhere it's defined, okay? The definition of continuity really depends on you understanding a limit, okay? What it means is that the limit as x approaches a of f of x is equal to f of a, okay? For all a in the domain. Okay, so this is a bonus question, so you're not assumed to know this, I guess. But if you know it, then this is what I think you're supposed to know, is that this function is continuous on its domain. Since -1 is in the domain, all numbers are in the domain, this limit can be found just by plugging in -1, okay? So if I plug in -1, whoa. If I plug in -1, what do I get? That's going to be -1 plus 5 over 1 plus 1. So that's 4 over 2. The answer is 2. Okay. Now, Daniel, I think what you were thinking of, I think you misread the question. I think you were thinking of the limit as x approaches infinity. That's what I think you were doing. In that case, you would be correct that the limit does not exist, and the reason is because the numerator has a higher exponent. That's absolutely right. So just make sure you're reading these questions very carefully, okay? That's always good advice. Okay, and in this one, okay, so again, I feel a little funny explaining these because you might not have seen limits before, but the trick here is to do some factoring. So if I consider this as the limit as x goes to 3 from below of, I'm going to factor the top to be x plus 3 times x minus 3 and leave the bottom as x minus 3. So now I see that there are some cancellations here, okay? Let's see, so when you do this sort of thing, you are making some sort of assumption. You're saying, well, let me continue writing. So this is equal to the limit as x approaches 3 from below of x plus 3, okay? The assumption that you're making, you've got these two expressions. Whoops, didn't mean to do that. You've got this expression here and you've got this expression here. And they're not identical, okay? When I make this cancellation, it's very easy to say, oh, the top thing equals the bottom thing, right? This expression here is equal to this expression here. Well, most of the time you're right. As long as if x is like 1 or 2 or 0, then you're right. This is going to give you some number, and this is going to give you the exact same number, because obviously that, you know, multiplying the top and the bottom by the same number doesn't change the answer, right? But what if x is negative? Oh, I didn't. Yeah. What if x is 3? If x is 3, then this is 6, correct? But if x is 3, then this is undefined. This is the one case where this extra factor of x minus 3 in the top and the bottom play a role, because then you've got 0 over 0, which is not defined. Okay? So these expressions are only equal when x is not 3. Okay? When x is 3, this one's undefined. You get 0 over 0 when x equals 3. Okay? But the bottom one is when x equals 3 is 6. There's no problem at all. Okay? But it's okay, because when you take a limit, okay, when you take a limit, this is x is getting closer and closer to 3. For this question, it really doesn't matter that it's staying below 3. But what that means is that we're plugging in numbers like 2.9, 2.99, etc. Okay? We're not going to plug in numbers like 3.1 and 3.01 because we're going to approach 3 from below. Okay? But the point is that when you, since you're not plugging in 3, you're only plugging in numbers that are close to 3. Okay? When you plug in 2.9, you get out 5.9. When you plug in 2.99, you get out, when you do this, x plus 3 is going to equal 5.9 here. It's going to equal 5.99 here. It's going to equal 5.999 there. Okay? It's really easy. I think it looks like these numbers are approaching 6, right? Well, that's none of the above. Did I do this correctly? I guess it takes some courage to put that answer down there. Even when you're very, very, very confident, it still makes me doubt myself. But I don't think I've made a mistake. I do make silly mistakes and turn pluses into minuses, but I don't think I did in this case. I think I'm very good here. So I'm gonna put my answer of none of the above. But for the record, the answer would have been 6. And that's the last question. Okay, so I'm happy to go over any of these questions in more detail, or any of the topics that I mentioned. If I'm scrolling through this, what topics were covered on this quiz? Clearly exponential rules, right? Maybe we should make a short list at the bottom, okay? So what were we talking about in this quiz? What are you expected to know coming into this class? Clearly exponential rules. Okay. What else? Let's see. What else? Besides exponents, that includes negative exponents, of course. Let's see, how do I classify this one? Well, it's basically, I mean, it's factoring, I think. Still exponents. And then, okay, logarithms and exponential functions. Okay, we can add that to the list. Okay, and the important things to understand with that log base a of x equals y is the same thing as saying a to the y is equal to x. Okay, to make an analogy, you know, there's a relation between x and y. Okay, so x and y have some kind of relation. And there are two ways to say it. You can say that log base a of x is y, or the exponential base a of y is x. Okay, those are two different ways of saying the same thing. The analogy I usually make is that I can say, I can say he is my father. That's telling you the relation between me and another person. But I can also say that I am his son. Okay, so those are inverse. Those are inverse relationships. Okay, it's two ways. There's only one relationship, but there's two ways to say it. You can start with him and say he is my father, or you can start with me and say I'm his son. Just the way that x and y in these equations are related in some way, and there's two ways to state that relation. Okay. Okay, so moving on. There were a lot of questions about logarithms. There were a lot of log rules. Okay, so I should add log rules to that list. Not just, this is really more about the definition, but specifically, you should be experts in log rules. Okay. And what else? That's basically it. I mean, the bonus had a lot of questions about limits, so I guess we know where you're heading in this class. So coming up are limits, but I'm not going to put that on this list because I don't think you were assumed to know that. So these are the topics that I mostly saw in this quiz. I'm happy to go over any of these topics in more detail if you want. Let me know if you do. But otherwise, I'm ready to end this class. Okay, so I assume you guys are meeting a week from today. I shouldn't say anything. I don't really know. But I did hear Jhevon say that you have some video lectures to watch tonight. So we should watch those, and I'll send you on your way. You're welcome to stick around and ask questions if you have them. But otherwise, good luck to you guys. I hope you enjoy the semester. I know you're in good hands with Jhevon. He's an excellent instructor. So best of luck to you guys. Take care.
Thank you.
Thank you.
Thank you.
Mary and Sophia, do you have questions? Okay, maybe you just stepped away. I'm going to end the meeting.